U to R. So assume this is open. Well, you take just some interior point in here, A in U. Now, you assume that F is differentiable at U. Now, the gradient of F at A, I'm set, the point is A. This is defined as and you assume that the gradient at A is different than 0. Now U bar is given as the gradient divided by its norm. So you make this, okay? And now the question is, for all U in RP, the F of A U is, so the F of A is a linear map on RP to R, so this is a real number. This is less than or equal to the F of A at U bar. This was the question, right? Okay. Now, what's the F of A at U? So, the proof will be shorter than this. What's the F of AU? Well, it's the Jacobian times the column matrix U, which is the same as the inner product of this with U. And well, here we take this to be 1 as well. Otherwise, I mean, it will not. So you make them all of length 1. But this is an inner product. What do we know about this inner product by Cauchy-Schwarz? It's less than or equal to the norm of F of A times the norm of U, but that's 1. Okay? Now let's compute the FA at U bar. That's del FA, the inner product of this with U bar, but U bar is but this is just the norm of del FA, and we know that this is larger than or equal to the F of AU. So the F of AU for any U with norm 1 is less than or equal to the F of AU bar, which means you're at the point A, you move away from that in some direction. The directional derivative, now the direction vector being normalized with norm 1, when is it largest? It's in the direction of the gradient. So that's what the information this gives us about differentiation. But here in the proof, you don't use, well, you just, of course you use, I mean, we spent quite some time to prove that this holds, okay? But given that, now, Is it okay now? Yeah. Okay, then let's start with the exam. Now, as I will be sending you fully written solutions, most probably before Tuesday, so I will just do it in a sketchy way here. In fact, rather than writing a full solution, we will discuss how to discover the solution. That's maybe more important. Now, 1a, now we have this, phi, now from R2 to R2, into R, so this is a candidate for an inner product on R2. It's given by phi xy. X is x1, x2, as usual. Y is y1, y2. And this is defined as x1, y1 squared plus x2, y2 squared. Is this an inner product? Well, the first time while I was about to ask, well, is there an inner product whose value is always non-negative? Forget about this. Can there be an inner product on R2 or on some set, on some real vector space, such that x dot y is always larger than or equal to 0? That cannot be the case. Well, if you have the scalar multiplication, here it says c times phi xy, that's equal to phi of cxy. Suppose phi of uv is always larger than or equal to 0. This will be larger than or equal to 0. This will be larger than or equal to 0, but take this minus 1. So, well, then, for this, well, you can take x equal to 1, 0, y equal to 1, 0, c equal to 1. Now, phi xy, c times phi xy. Now, xy is 1 plus the square. 1 times 1, that's squared. That will be c times 1. That will be minus 1, but phi cxy, that will be what? C is minus 1, 0, but that will be just 1. Okay? So these are not equal to each other. Well, you can also give an example to show that this is not satisfied either. X, y plus z, that's supposed to be phi xy plus phi xz. This is not satisfied either by this. Okay? But the easiest way is this. Any questions? The second one is B. Xm, a metric space, A here, and the idea is to show that thought of asking, well, prove or disprove, but this was short at results. Did you get this all? This can be actually, to a very extreme extent, take RD, let A be the set of rationals. What's a closure? The entire R. What's the boundary of the entire space? That's always empty. Because the complement of the entire space is empty. Any neighborhood intersected with the empty set will yield empty, cannot be non-empty. So this will be empty if it's a closure. What about the boundary of A? When A is the set of rationals and the metric spaces are under its usual metric, the entire R. Because if you take any point, rational or irrational, and if you take any neighborhood of that, it will contain both, or any epsilon ball, in a metric space we can do that, any epsilon ball, it will contain both rationals, will have a non-empty intersection with cap A, and also irrationals, it will also have a non-empty intersection with the complement of Q. So, okay, now let X in del A bar. Suppose X is not in the boundary of A. Well, then that means there is some neighborhood U of X, either the intersection of U with A or its intersection with X minus A. One of the two should be empty. Well, this means there is some neighborhood U of X with U intersection A empty or U intersection X minus A empty. I'm sorry. Now, can we get some information from here? This is the same X, whether this or this cannot hold. Now, A closure that contains A. So X minus A closure, that's contained in here. But this says U is some neighborhood of X, U intersection X minus A closure is non-empty. But if this is non-empty, the intersection with this, well, then this has to be non-empty as well. So this cannot be the case, since X is in del A bar. Is that okay? X is in here, U is a neighborhood of X, so U intersection A bar, that's non-empty. U intersection X minus A bar, that's non-empty as well. But this U intersection X minus A, here you're taking out something smaller than A bar. So this is a larger set. This is non-empty. This has to be non-empty. So, well, the neighborhood U of X with this or this cannot be the case. So it must be this. But what does this imply about the relationship between X and A? You have some x, which has a neighborhood, which has an empty intersection with A. This means x is not a limit point of A, because a limit point means for any neighborhood U of that point, that has to have a non-empty intersection with this. So this means x is not a limit point of A. But what's the set of all limit points of A? That's just the definition of A closure. So X is not in A closure. But what do we know about A closure? X is not in A closure. It's closed. So this X has some neighborhood or some epsilon ball, we have some neighborhood U bar such that U bar intersection A closure is empty. But then how come can X be in del A bar, a boundary point of A bar? So this implies X is not a boundary point of A bar. Contradiction. So this supposition must be false. Okay? Then C, now that was, I guess, you have an example of a topological space, a subset A of X, if any, such that A is compact, del A is the entire X, and A interior is empty. What was your example in the exam? There are several examples, but this, yeah, well, just take X equal to 1, 2, and tau phi cap X, and A just consisting of 1. Is A compact? A is compact for several different reasons. Well, any subset under the indiscrete topology is compact. Any finite set is compact. So this is compact. It's finite, it's compact under any topology. Under this topology, anything is compact. So it's compact. Is its interior empty? Yes. The only neighborhood of 1 is the entire space, and that's not contained in cap A. So the interior is empty. Is the boundary the whole space? Well, since the only neighborhood is a 1 is, well, a 1 or 2. Either 1 or 2, well, they both have just one neighborhood. That's cap X. But cap X intersects both with this, and its complement is non-empty as well. It intersects with that non-emptily as well, so anything is a boundary point. So this holds as well. D is interesting. For what? Rho, this is on R. Rho xy is equal to x minus y plus 1 if either x is positive, y is less than or equal to 0, or x less than or equal to 0, y 0, and x minus y otherwise. So here, this is 0 if your 2 points belong to this part, then you have this. Or if they both belong to this part, then you have again this. But otherwise, if one is positive or negative and the other is non-negative and or non-positive, then the distance is large. Well, why do we work with such weird topologies or metrics here, you might say? Well, this is like, well, I mean, Berlin is not divided anymore, but Nicosia is divided. You have the green line. If you're in the north both and spatially close to each other, you're close to each other. If you're both in the southern part, then you're close to each other if you're spatially close to each other. On the green line, you have United Nations soldiers. They are close to both sides, but if one is in the southern and the other is in the northern part, in order to reach, well, a Greek guy, has to fly to Athens first, then to somewhere in Turkey, and then to northern Cyprus. They're far away. So this is actually a metric. It's really, if you have some barrier, if you're on one and the same side of the barrier, you're close. Well, if you are close spatially, you're really close, but if the barrier is in between, then you're not close. So that's to represent that situation. Well, it's larger than or equal to 0, clearly. If x is equal to y, then you cannot have either this or this if x and y are the same. Okay, so you have to be in here, then this is 0. If x is equal to y, okay. And if rho xy is equal to 0, you cannot have this case. You must have this case, but then x will be equal to y. Well, xy, yx, well, if you interchange x and y, you'll switch from one case to the other if you're in this case. Well, if not, then you stay within this case. So that's also true. And for the triangle inequality, well, you can, if you wish, consider all cases separately. But we had similar examples, and, well, the easiest way is, now you take x, y, z, and you wish to know whether this is less than or equal to rho xy plus rho yz. You check this.
If all of them are less than 0, you have only the second one, and all of them greater than 0, you have absolute value of x and y. So we check only like for 2 cases.
Yeah. If okay, well, or here if rho xy is equal to x minus y plus 1, or rho xz is y minus z plus 1, that's one case. Then rho xz, that will be less than or equal to x minus z plus 1. It's either this or this plus 1. Okay? So it's less than either this or this, but this will be less than or equal to x minus y plus y minus z plus 1. And this will be, in fact, less than or equal to rho xy plus rho yz, because you might have 1 from each, but 1, 1, that suffices. So for this. Otherwise, if the second case is rho xy equal to x minus y and rho yz is equal to y minus z. But if they fall, if x and y, well, they neither here nor here, this is neither there nor there, so you have also rho xz equal to x minus z. Okay? And that does the job. X minus z will be less than or equal to the sum of these. Everything reduces to this part. Any questions about this? E. This time, the answers actually were short all. E. It's what? Now, x, you have M, a metric. X is not bounded with respect to M. Can we find rho equivalent to M, a metric rho, such that X is bounded with respect to rho? Can we? Minimum of 1 and rho of xy equal to the minimum of mxy 1. We had this example for in the case of the usual metric in R and so on, but well, you can, if you take all your epsilons less than 1 in a metric space, you can do, okay, openness, well, that does not for large epsilon, but if you take all your epsilons less than 1, then M and rho coincide for those. I mean, you have to, of course, show that this does formally, but the idea is, okay? Are you convinced? Okay. Next. Here, X, non-empty set. Here, Y is contained in X, and tau is 2 to the Y union this set X. Well, that this is a topology is clear, I guess. The empty set belongs to this. X is explicitly in there. If you take a whole bunch of sets from this collection, well, if one of them is cap X, then the union will be cap X. is none is equal to cap x, they will all be subsets of cap y. But if you take the union of subsets of cap y, that's a subset of cap y as well. And well, A intersection B, if it's either a, well, well, if one of them is x, then you will have A intersection B equal to either A or B. That will be in tau. Otherwise, A and B are both subsets of Y. A intersection B will be a subset of Y as well. Okay? So that's a topology. So it says two parts. Find given example of Yx and under this topology such that tau turns out to be metrizable, and for the other case, non-metrizable. Is it ever metrizable? With this condition. We have this condition. Huh?
If it is empty and x is one.
That's non-metrizable. Well,
X is one element.
But then this should be non-empty. Okay.
X is one.
Okay, X has one member. Okay, in that case, it's metrizable. Only in that case. Because you have to take this the empty set. Well, the discrete, indiscrete topology, all topologies, they coincide. All metrics, if the set consists of one point only, that's the only example. Otherwise, it's always non-metrizable. Why is that so? Well, if X has more than one member and Y is empty, what's the topology? That will be the indiscrete topology in that case, because phi is the only subset of phi, and you have cap X, and you have at least two members. Well, we know that that's not metrizable. We have seen that. Suppose Y is a proper subset of cap X, and Y is not empty. Can that be metrizable? No, here, this is X, this is Y. You have at least one point here. The only open set which contains this point will be the entire set. So if you take a point here and another point, be it here or here, makes no difference. If it's metrizable, you can separate them. You can find epsilon balls about them such that the intersection of the epsilon balls are empty, is empty, but you cannot separate them here. So it's, except for the case, this is a one-element set and this is the empty set, it's not metrizable. Okay? So any example will do for that case, but of course, you have to show that it is so. Any questions here? Okay. Now, part C, find the closure of Y bar and this. Well, if something is in Y, that will be in Y closure. So consider something not in Y. Will that be a limit point of Y? Well, to check, take any neighborhood U of that point. What must U then be? Well, it must be cap X. The intersection of cap x with y, if y is non-empty, will be non-empty. So everything will be in the closure. If y is empty, of course, then y closure, that will be empty in that case. What about the boundary? Well, consider a point belonging to y. Can it be a boundary point of cap y? No. Y itself is open. Just take y as a neighborhood of any of its points. The intersection of that with the complement of y, that will be empty. Okay? What about a point outside y? If y is empty, then its boundary will be empty again. So suppose y is not empty, and take a point in cap x, but not in y. Well, its only neighborhood is the entire cap x. Y is a proper subset of cap x. So there is something outside y, and there is something inside y. So those will be the boundary points in that case. Okay? Any questions about this? Question 3. You have two metric spaces. Then you take the Cartesian product of them and you define a new metric using these as the building blocks. You define for any Z1, Z2 in cap Z. Now this will be, Z1 will be X1, Y1, and Z2 will be X2, Y2. So here you define M Z1, Z2 as the distance between x1 and x2 according to rho plus the distance between y1 and y2 according to rho prime. Okay? Here you can think of this as follows. You actually attach two attributes to one and the same subject. Say, well, the tallness, the height of a guy and his or her weight. Well, then you first consider closeness in terms of heights and closeness in terms of weights. If they are close in both aspects, then they are close. But if they are close in one but not so in the other, well, they are apart from each other to some extent and so on. This can be taken to represent that where, well, I guess there's no problem in showing that this is a metric, so it's not interesting. It's very straightforward in this case. Now it says A is in X, B is non-empty in Y, A cross B is compact in Z with respect to M. A is compact with respect to rho. How did you solve this? How did you prove it?
Using the sequence.
I cannot.
The definition with the sequence.
The easiest way is using sequences. In fact, it becomes very easy in that case. You are supposed to show that A is compact. Well, in terms of sequences, what's the equivalent to that? Any sequence in A should have a convergent subsequence whose limit belongs to A. Well, take xn and check whether that's so. But what the information we have is in the product space. A cross B is compact. B is non-empty. So let me just take some y in B and let me consider the constant sequence y in B. And then x and y, that will be a sequence in A cross B. What do we know about A cross B? It's given that this is compact. So this will have some convergent subsequence whose limit belongs to A cross B. But in that subsequence as well, the cap y component of the sequence, that will be the same, y. And the distances, they get summed. Well, you will have zero contribution from here. So the only positive contribution will come from here. But that simply will mean if you now take apart the subsequence corresponding to xn, x bar n, that's convergent with respect to rho. And it will belong to A because the limit of this sequence, the limit of the convergent subsequence of this sequence belongs to A cross B. Huh? So the easiest way is to take constant sequence in B. So you do just you turn A cross B, if you reduce this to singleton, that will actually be a copy of A, the same thing as A. But of course, you have to do it, the formal things also appropriately. Okay? Any questions to this? Finally, 4. Well, I guess here, let me just say, unfortunately, there's a typo in C. It says that phi AB in X with A intersection B. Here, what it says is empty. It should be non-empty. A, B are both bounded. And the question is diameter A union B to show that this is diameter A plus diameter B. Well, if this is empty, then of course this does not hold. Take A point, a singleton set, B far apart another singleton set. The diameters of these two singleton sets separately will be 0, this will be 0, 0, but the diameter of A union B will be equal to this, and which you can make as large as you wish. Now here the idea is, if A and B have a non-empty intersection, then the distance from here to here will be less than or equal to the distance from here to here and from here to here. So that's the whole idea. The idea, well, but in such cases, well, if you take this seriously, what's written in here, and show that cannot be the case, then you'll get full credit. If you show that the question is wrong. No question about it, but we'll discuss 4. We'll start on Tuesday, we'll have just 1 hour. We'll start at 9:40. For 10 minutes, we'll discuss this question 4. Hopefully, you will have received the written solutions by that time. And then, well, we'll have a general assessment about mathematics, what we aimed, what we have achieved, what not, and so on. Okay. So that will be the closing session. I guess we can stop at this point.